It's a pleasure to welcome you all to the first colloquium of this fall. We have Professor Toomre1 from Colorado University of Colorado, Gila Laboratory. And Yuri has been involved in a number of very important projects in the US, but of this worldwide importance, of course. One of them being a co-PI on the MDI mission, that is a mission which the microton Doppler imager, which measured the oscillations of the solar surface in the so-called SOHO satellite, which is in between the Earth and the Sun, in a Lagrange point. So these are one of the big sources of information with which we can learn about the interior of the Sun. Yuri has also been involved over the decades in large-scale simulations and computations of the Sun, using simulations in global geometries and local geometries before that time. Yuri did his MSc at MIT in '63, and then his doctorate at Cambridge University in '67, and moved then in '75 to Gila, where he has been professor ever since. These are probably the most important stages of as far as that is concerned, but he has also been involved in a range of different projects, grand challenge projects, where one is looking for the scientific projects that can make use of the largest computers that we have in the world available. So these are still the sort of things that strive Yuri's imagination to go to a deeper and deeper understanding of the Sun through simulations. Yuri will today tell us about the sources of solar magnetism, using both his simulation skills, but also the skills in interpreting data through helioseismology. Yuri, please.
Thank you. Well, Yuri has another distinction. He's actually a Scandinavian. Well, sort of. I'm Estonian by birth. So I had the pleasure of visiting Tallinn for about the third time in my life just last week. But I have a great empathy for this part of the world. Is the sound level comfortable? Because various things were adjusted. Fine. Well, let's just start talking about what the Sun is all about, as if you know it anyway, but let me remind you of some bits and pieces. The Sun, of course, has nuclear burning at its core. It occupies the inner sort of 15–20% here. Radiation suffices to carry that radiation outwards until essentially the opacity of this plasma becomes such that you would, in the absence of convection or other things, the stratification would become superadiabatic and thus unstable to convection. The outer 30% of the Sun, by radius, in fact, is convectively very vigorous, highly turbulent motions that basically carry all of the flux in that region until you again hit the surface of the star and then radiation takes over. We've known this for a long time. I'll tend to sort of slip in some numbers. I could quote things in meters or in centimeters. Let me quote things in megameters, or 1,000 kilometers. Because, in fact, this dimension of the Sun is 700 of those. It's kind of a convenient number. And the depth of the convection zone is about 200 megameters, or 30% of that radius. The thing that is really distinguishable about the Sun is that it exhibits a very large range of dynamical scales of motion when we observe its surface. We've known for a long time that there's granulation that has a 1,000 kilometer or 1 megameter scale. There are mesogranules that are about 5 megameters that last rather longer. The granules are visible for about 10 minutes. These for 2 or 3 hours as reasonably distinct entities. Supergranules they're of the order of 20 megameters, and they last for several days. Typically 1 day, but up to 3 or 4 days. Cellular motions that are fairly discernible, and in fact sweep magnetic fields to their boundaries and thus are visible in some spectral lines. And one expects that there are also things that might be called giant cells that would reflect something about the overall geometrical depth of this layer. So there should be probably scales of convection that span the full depth of this convection zone probably and have large scales. Well, all of these things are running at the same time. one might say, well, so what? The interesting thing is that we've known for a long time that the Sun exhibits a strong differential rotation, in the sense that the equatorial regions rotate once in about 25 days, and the poles in about 33 days. So possibly a question of interest is, how does this result? Why is it as stable as it is? And what are its implications in terms of what goes on in the interior? And although we've known about the differential rotation for well over 100 years, it wasn't until helioseismology came along that we could also see what the nature of the differential rotation was below the surface, because we could sample that region. And there were some significant surprises about that, which I'll talk about in just a minute. Why do we care about all of this? Well, in some ways it's fashionable to deal with order amidst chaos in dynamical systems, and the solar convection zone certainly exhibits some of those features. And in many ways, if we were to measure the properties of this turbulence, it has about the highest Reynolds number of anywhere in our near universe. The Reynolds numbers are probably 10 to the 15, 10 to the 17. Those are ratios of the nonlinear terms, the diffusive processes. And we know that there's generally transition from laminar to turbulent flows when that is around 1,000. So we're quite a few decades away from where you would think that you really start things cooking. But what is interesting is that amidst this very vigorous, highly turbulent zone, you end up establishing a fairly orderly and strong differential rotation, for one thing. And we believe that this rotation plays some fairly subtle role in why it is that the Sun exhibits global magnetic cycles and dynamo action. Our motivation would be to at least understand how that various aspects of the solar magnetism is realized, and possibly it would be in a position where we could at least maybe even be able to predict what its behavior would be, although that might be a very difficult thing to do for it to be practical. But I should just emphasize that the magnetism we see comes on a huge range of scales. If we take any soft X-ray images of the Sun, sort of global views, we see large structures throughout. But when we go to something which is a region about the size of this laser dot, and zoom in on that, the granulation becomes visible. These are these dark regions of probably downflows and upflows, but the magnetism ends up being at many of the points between these cells. They evolve fairly rapidly, but it looks like the solar magnetism is very fractal. It organizes itself into large blotches, but it has almost a fibril nature everywhere. So you can have large cables of these things, but there's also very fine scale structure as we get to higher and higher spatial resolutions. So this scale is 1 megameter, and from the best ground-based observations we can see that some of these magnetic structures are of the order of 50 kilometers across. But there are also much larger things. The sort of beautiful imaging from the new Swedish Solar Telescope on the Canary Islands emphasizes that the types of sunflowers that Van Gogh favored, the Sun also favors. This is the granulation, but of course we have much larger structures having to do with the dark umbral and penumbral regions of the magnetic field. And of course all of these filamentary structures are basically representing something about the magnetism. And in fact, each of these ticks has a 1 megameter spacing, just again to be convenient for scale. And there's clearly a very complex interplay between the convective motions themselves and the magnetism. Solid convection is suppressed in these regions of magnetism. How strong are the fields? Well, the fields here in the center can be of the order of 3,000 Gauss. You know, the average field of the Earth is 1 Gauss. The average field of the Sun, if you average over the entire Sun, is 1 Gauss. But in places where the magnetic field is strong, it's 1,000, 2,000 Gauss, even in these very small features. So why is it that you have these very intense fields, and sometimes the intense fields, small fields, are organized as these large structures? Now, if we were to cycle through a spectral line like H alpha and said, fine, here's what it looks like in continuum, and here's the Earth in comparison for size, as we move through this spectral line, which is formed higher in the atmosphere, you begin to see that there's large-scale connections that are must be related to how the field itself is connected to other sites. So that even though the fields are localized, they have often large-scale structuring throughout. Sorry, this projector isn't showing quite the contrast range, but perhaps it sufficiently makes the point. If we go into soft X-ray imaging from satellite experiments, one of these is the trace transition region, essentially an explorer mission, and this is the limb of the sun. It emphasizes that very frequently you see great arcades of field. Probably is field that you're lighting up, the plasma is particularly responding, but what's striking is that the fields are yet very narrow structures everywhere. They don't kind of open up into broad envelopes. They're structures of fine scale in most sites. And they must be related to how the fields themselves emerge from the surface at the sort of the granular scales and the other organization that occurs. And similarly, when we take some of the sort of images, again from space, very often one sees large ejecta, but they're basically big magnetic loops. That may involve the release of a few billion tons of plasma. And of course there is some interest because if they arrive here, a few do, as in this sequence of images, again taken with the SOHO spacecraft, the sun is here, one has blocked out some things to keep from confusion, but the rest are basically in the EUV range. It emphasizes that you often have large ejecta, which have come to be called coronal mass ejections. Many of them go in other directions, like this one. But these releases of a few billion tons, if they come into your face, you can shut down satellites, you can electrify power grids, do interesting things, turn off the ability to pay with your credit card at the gasoline pump, which are actually done by satellite communications for most places. So it's of some mild concern. But what the spacecraft experiments have also done is that if you look in the 195 angstrom range at the sun in sequence and time of SOHO, in the last 2 weeks of 1999, one was wondering if we could survive the Y2K problem. It emphasizes certainly the sun rotates, but all the structure that we're seeing is really that from large magnetic arcades that largely fill the space. Now, as we just got past Christmas, there is a large dark region arriving, which maybe portends of the end of the universe, at least of this millennium. And the movie does stop at the end of the millennium, and the dark side has appeared, but we seem to survive. Now, the main things about this sort of global scale magnetism is maybe done by looking at, say, movie sequences of what the magnetism looks like. With the SOHO spacecraft, we can get an entire sort of magnetic image. The blue and yellow here refer to regions of fairly strong field of opposite polarity. David Hathaway has animated these things. So if I can find where my mouse has gone. Come on, Mosi. Again, the sun obviously rotates, but we can turn this into sort of a longitude-latitude map, which it is right now. The equator is here, longitude is that way, and then animate it, which emphasizes that we go through cycles of behavior. That early in the cycle, the magnetic fields emerge first around sort of 30 degrees latitude, then migrate gradually. They begin to appear closer and closer to the equator, and then they go away again and then come back again. Well, we've known about these cycles of activity for a long time. We run it just once more. But the interesting thing is this magnetism has some very good rules in terms of where do the so-called leading and trailing sunspot appear relative to each other, how they're bent, called Joy's law, the fact that there are cycles. Why is it that the global magnetism of the sun, which is related to these appearance of sunspots, has a behavior of this sort? Now, we've given some of this stuff a name, butterflies. The sun clearly exhibits 11-year cycles. If you were to map as a function of time by year, where the sunspots particularly appeared and assign some color to it, where you think it was entirely on that, on a given latitude circle, then you get things that have some semblance to the wings of a butterfly. Or similarly ask, well, what's the number of appearances of sunspots as a function of cycle? The main thing is that it takes two of these to bring you back to the original magnetic field. So the sun runs about a 22-year cycle. It isn't entirely tidy, but these successive things come and go, but they've been running. Now, of course, shortly after Galileo first saw his version of the sunspots, the sun also went fairly quiet in the Maunder minimum, which maybe was a disappointment. But in the large, the eruption of field satisfies rules like this. And where are we now? Well, we're probably close to the minimum, or maybe we've already passed the minimum, and we're starting to climb into the next cycle. What are all of these things? Well, we think that the operation of the global dynamo has a number of elements that are maybe suggested in this cartoon sketch. We certainly have a photosphere from which we see large loops of magnetic field emerging, which then leads to two sunspots, the leading and the trailing spots. The convection zone itself occupies, as we said, about 30% in proportional radius, a major ratio of density contrast across fully compressible stuff. There's rotation. We think there's various forms of local dynamo action that occurs in this turbulence, but because of the nature of the highly compressible convection that it takes, it has a possibility of pumping some of those magnetic fields downwards, because the downflows are shorter, narrower, and faster than the outflows. And we'll show you some of these aspects. But the surprise from heliosmology that I'll show you in just a few minutes is that at the base of this convection zone, where we go from essentially the radiative interior to the convection zone, there's a region of strong shear that has been shown to be present by heliosmology, and has come to be called the tachocline. Tacho meaning speed, cline layer of change. And that had not been anticipated prior to the work with heliosmology about 20 years ago. But 20 years is a long time, but we've done a lot of study of what are the properties of the stability of these tachoclines and things like that. We think that the shear that I'll show you has the possibility of combing or organizing some of the magnetic field that gets pumped into that region to build presumably fairly strong toroidal fields, ones that extend in longitude, to the point of where they may experience magnetic buoyancy instabilities, because these structures themselves, if they have field strengths of 100,000 Gauss or so, and if there were to be a balance between magnetic pressure plus gas pressure inside the tube and gas pressure outside, there must be partial evacuation, lower density in some fashion in that tube. At some point it could experience buoyancy instabilities. And some of these structures are likely to rise. Some of them get shredded. They certainly sense rotation. Some will make it. Some gets recycled. So we think that there are a number of elements that come into how the large global dynamo is operating, and we have some ideas of how some of them work, but these are basically still cartoon sketches, but they're close links with heliosmology to at least inspire some of the thoughts. So what's heliosmology? Well, it isn't entirely the digging of tunnels beneath the surface. It's very nice to have. These are localized sources of noise. You know where it is because most of course, geophysical seismology works on the same principle, that you have discrete, localized sources, then you look at the response. Here in the sun, the turbulence that occupies this outer 30% has the characteristics that it's very fast compressible motion just below the surface. The Mach number of those motions are about 1/10, 2/10. And if those motions are fast, which is basically convective in origin, it'll also make sound. So they happen to be very efficient sound makers, and I'll show you what some of that sound looks like. But it's distributed everywhere, that at any given time you might have things with spherical magnetic degree of about 4,000, which is the nature of the scale of granulation, pummeling the surface, contributing sound, among other things. Now, we might say, fine, well, what are these sketches here? Well, here's a cross-section cut of the sun, and really just ray diagrams. And the way that at least the acoustic oscillations work is very simple to understand. Namely, if we look at a phase front in a sound wave, if it were traveling perfectly radially inwards, the travel time from here to here is 55 minutes. Now it's a big sun, but it mostly is able to do that because the speed of sound here at the surface is 7 kilometers per second, and here it's 220 kilometers per second. And so the fact, and why so? Well, it's mostly that the temperature here is about 6,000 Kelvin, and it's about 16 million Kelvin here, and the speed of sound goes roughly as a square root of temperature. Composition plays a role too. So if a sound wave is traveling straight in, it just goes right through and then bounces off the other side. I mean, there's reflection just below the surface because the scale height shrinks rapidly, and if the wave has any significant vertical extent, it'll bounce, almost a WKB reflection. But if the phase front is slightly tilted, it of course has the aspect that the deeper portion of the wave experiences a slightly faster sound speed, and it'll just turn these phase fronts around until it is moving horizontally, but then it keeps shifting, of course. So there are some waves that just noodle below the surface. There are others that go scraping in. There are very few that make it all the way to the center because the number of rate paths that are allowed gets to be kind of small. Of course, the rate paths don't tell you what the eigenfunctions look like, but the principle of why we can do things with heliosmology is simply because of the stratification in sound with depth. It's monotonic. Fast sound speed inside, lower outside. There's also a possibility that you could have some internal gravity waves which make very pretty shapes, but we really haven't clearly detected them. And one of the problems may be that the internal gravity wave, which could be supported on the inside, then has to tunnel through the unstable stratification here, and there's basically exponential attenuation. We would love it if we could detect the internal gravity waves, but so far I would say in a way where it has diagnostic value, we haven't seen them. They could be excited by the turbulence. So just a few words on how this thing works. Well, fortunately we're able to do a lot of stuff with heliosmology, mostly because we can do linear theory. That we'll find out that the composite signal from the acoustic oscillations at the surface is about 1 kilometer per second, 1,000 meters per second. But we think that the individual modes contributing to it, and it's just random interference, have amplitudes of about 1 meter per second. So if you took 1 million modes of 1 meter per second and asked, well, what's the most likely RMS value, it would be 1,000 meters per second, roughly. Well, the modes have actually slightly smaller amplitudes, more like 20 centimeters per second as seen at the surface, and there are rather more of them. But any one of them could be just simply described in terms of a spherical harmonic function on the surface, and then what would be the radial structure as it goes inwards. The ray diagrams don't show you that you have multiple nodes in the radial structure, but of course you can. You're running various overtones in those modes. So just a few comments from linear perturbation theory. We might say, look, let's look at the radial velocity in this stuff. Well, we decompose it in terms of spherical harmonic function involving L and M as the spherical harmonic degree L and azimuthal order M, that has some radial eigenfunction to be solved for, and then a temporal frequency involving nu. And so you might say, fine, you have 3 quantum numbers that tell you about the spatial structure of the modes in terms of how many nodes there are in a great circle and what the orientation of that is. And then you go solve for the radial order of the mode, and out of it comes a frequency. And so we have effectively a few million of these modes. Could be larger, but observable is of that order. So if we went and then solved for the eigenfunction that goes along with this problem, taking what we think is a realistic solar stratification, and then worked out what the frequencies would be, well, the eigenfunctions tend to be that if this is the surface and this is the center of the sun and this is the depth of the convection zone, there are lots of wiggles near the surface. This is a mode that has 19 internal nodes, whereas its spherical harmonic degree, horizontal, is only 10. All the acoustic modes have wiggles near the surface. They get reflected, and some go a short distance in, some go a greater distance in. We could really work this thing out technically it turns out that very many of the acoustic modes we're looking at have a period of about 5 minutes, or 3 millihertz or 3,000 microhertz. And here are a series of modes with spherical magnetic degrees 0, 20, and 60. They all have about the same frequency, but they differ in terms of their radial eigenfunction structure. And if you say, well, how do you determine that frequency? Well, you do so in some composite integral of what the sound speed is from here to the bottom, or from here to the turning point, or from here to the turning point. And in a way, if we had access to many of these modes, we could take information from various of these eigenfunctions to sort of try to build localized delta functions, and that's what inversion does, to be able to sort of try to estimate what the sound speed would be, not from here to here, but at some given location. And that's the power of the method. If you had only one mode to work with, not much use. But if you had access to a large number of oscillation modes and could measure their frequencies very accurately and knew what their quantum numbers were, you could do inversion of the structure to figure out what is the radial stratification of the sun. You could also look at large-scale flows within the sun because of certain degeneracies between modes that are traveling east versus traveling west. They will appear to you to have slightly different frequency splitting. Well, so what do we do? Well, we have a series of observing systems that are running right now. They're both using a small cube, which is basically a Michelson interferometer. This is the size of our quarter and your corona. But they're elegant instruments which allow you to measure the line of sight Doppler velocity of the sun with a precision of about 10 centimeters per second out of a very large range. You're going to a particular spectral line, and you're able to form a Doppler image effectively, line of sight velocity from certain spectral lines over 1,000 by 1,000 points every 20 seconds, if you want to do that.